Since this ion selectivity is so important, it's worth a short detour to talk about how on Earth nature achieves a channel that can let potassium pass through, but which blocks sodium. Now, it's easy to imagine how you'd make a channel that blocks, say, all positively charged ions. For instance, if we put a positive charge somewhere in the pore, we could rely on electrostatic repulsion to keep the positive charges out. But that's not what we need to do here. Both potassium and sodium are positively charged. So we need to somehow sort them based on their size. This is where things start getting crazy. These things are tiny, absurdly tiny. The ionic radius of sodium is just 116 picometers. That's about 1/10 of 1/1000th of a meter. A potassium ion is just 152 picometers. So the difference between them is about 1/20th of 1/1000th of a meter. And we need to sort them. The solution is nuanced and kind of cool. Do you remember how we said that positive and negative charges attract? Well, if we have a positively charged ion diffusing around in water, it doesn't travel alone. You see, the water, H2O, while net neutral, has a polarity to it. The oxygen bit tends to be more negative, and the hydrogens tend to be a bit more positive. So when we have a cation in solution, the water molecules are happiest when they point their negative ends towards the cation, and their positive ends away. The result is a sort of shell of water molecules surrounding the cation. We call this shell a solvation shell. Everything at a molecular level is about driving towards the lowest energy configuration, and the solvation shell for a particular cation is in its lowest energy configuration at a very particular spacing, where the interactions between the negative ends of the oxygen and the cation, and the interference and electrostatic interactions between the water molecules just balance out. It's one characteristic spacing for a potassium ion, which has a particular size, and it's a different configuration for a sodium ion, which has a slightly different size. In solution, the water molecules are free to situate themselves wherever, so these solvation shells just form, and that's that. But nature has arrived at a very clever trick for leveraging this phenomenon to build selective ion channels. You see, the channel, which is made of protein, has a special mechanism in front of its pore called a selectivity filter. This molecular machine exists to do one thing: simulate the spacing of the solvation shell in a fixed configuration for its ion of interest. So the protein includes carefully placed amino acids in its structure that reproduce the spacing and charge of the naturally occurring solvation shell. The result is that while potassium can happily exist in the space of the simulated solvation shell, and there it can diffuse through, the spacing is just a bit off for the sodium, making it energetically unfavorable for it to even go through the pore. It's sort of like a carefully tailored glove, made to fit just one person's hand. Truly amazing stuff.